Hello everyone, how are you all? I hope you are doing well. I am Dr. Nandita and I would like to welcome all of you to Aptdemy. But before I start today, I would like to share with you some information or maybe online registration in Aptdemy has already started. So you can go to our website www.aptdemy.com and you can get registered there. And after registration, you can get access 24/7 access to all the course materials. So today I am here in this live session to solve very interesting some numerical problems on the concepts that you have learned in the chapter solutions. And this session has been organized on the basis of some students' request. So get registered and get connected with Aptdemy and let's get started with the problem. This problem has been taken from Joint Entrance Advanced Examination 2022 and this problem is based on the concept of solubility. But before I go into the problem, let's just talk a little bit about the concept of solubility. So what is actually solubility? Solubility of any substance is the ability of that substance to be dissolved in a particular solvent at a particular temperature. So if it actually depends on the interaction between the solvent particles and the solute particles. If the interaction between the solvent and solute particles are strong enough, then the solubility of the substance in that particular solvent is high. But if the interaction between the solvent and the solute particles are weak, then the solubility is poor or low. Now, in your day-to-day life, you are actually observing several phenomena where you can directly apply the concept of solubility. So it is not only for the chemist but for all the people. So whenever you are making sewer solutions or salt solution in water at 20 degree centigrade or around room temperature, you actually can be able to see that they are completely soluble in water at room temperature at around 20 degree centigrade. So this is the concept of solubility. Now, if you are having powdered juice, you also know that powdered juices are actually soluble in water and they are containing sugar powder, some flavorings and some other chemicals. They are called preservatives. So if you, they are also soluble at room temperature in water and thus you are getting the powdered juices in your dissolved in water and you are having the juice. Right now, whenever you are washing your clothes, you are actually dissolving your detergent to the water and you are making foams and thus you will be able to clean your clothes. Another example could be that any cleaning agents at your household stuffs, it could be dishwasher cleaning, it could be floor cleaners, they are containing nitrogens and they are actually dissolving in water. Let's take the final example in aquatic environment where oxygen is getting dissolved into water and thus it helps for the aquatic plants or animals to breathe properly. So these are the very common examples that you are observing in your day-to-day life based on the concept of solubility. Now in this problem, we will be talking about the solubility of electrolytes who are actually getting dissolved in water and getting dissociated into ions. So we will be talking about two electrolytes H2SO4 and NO2SO4. Now without further delay, let's get started with the problem. So the problem 1 is asking that concentration of H2SO4 and NO2SO4 in a solution is 1 molar and 1.8 times 10 to the power minus 2 molar respectively. Molar solubility of lead sulfate in the same solution is X times 10 to the power minus Y molar. expressed in scientific notation. The value of Y we have to calculate. Some other informations are given. Solubility product of lead sulfate, that is KSP, is given as 1.6 times 10 to the power minus 8. And also it is given that for H2SO4 Ka1, that is the acid dissociation constant, is very large, and Ka2 has been given as 1.2 times 10 to the power minus 2. Now let's see how can we be able to find out the value of Y. So because we are talking about the dissociation of the electrolyte H2SO4, and because we are having two hydrogen here, so it will be dissociated into consecutive reactions. So the first one is H2SO4 is getting dissociated to give you H plus plus HSO4 minus, and Ka1, that is the acid dissociation constant for this particular reaction, is given as very large. The number is not given. Now, the second one, HSO4 minus, would be dissociated as again H plus plus SO4 2 minus. Now, the SO4 2 minus concentration which is given here is actually coming from the Na2SO4, and it is also given that the concentration of H plus and concentration of HSO4 minus as 1 molar, right? So this SO4 2 minus is actually coming from Na2SO4, and its concentration then can be written as 1.8 times 10 to the power minus 2 molar. Now if you write down again in the form of dissociation from this particular equation, you will be able to write that concentration of H plus times concentration of SO4 2 minus divided by concentration of HSO4 minus is equal to, this is 1 as given, 1 molar, divided by 1 molar for HSO4 minus, and this is 1.8 times 10 to the power minus 2 molar, or 1.8 times 10 to the power minus 2. So here Ka2 for this one was given as here Ka2 is given as 1.2 times 10 to the power minus 2. So this is the acid dissociation constant for the second step, where HSO4 minus is getting dissociated as H plus and SO4 2 minus. Now, so from this you can easily able to comment that instead of dissociation of HSO4 minus into H plus and SO4 2 minus, it will be easier for the association of H plus and SO4 2 minus to form HSO4 minus. So instead of dissociation, association of H plus and SO4 2 minus in order to form HSO4 minus would be energetically favorable. Now, if we assume that if mole per liter of both H plus and SO4 2 minus are combined together to form HSO4 minus, what can we write is that the concentration of SO4 2 minus in that case is 1.8 times 10 to the power minus 2 minus x, because it is associated, so they are acting as reactant and this is acting as product. And similarly for H plus, the concentration we can write as 1 minus x, which can be equal to 1. And again for HSO4 minus, the concentration would be 1 plus x, which is again equal to 1. And this can be true only if x is much less than 1. Right? Now, if you put the values for this dissociation step of second step, then what we will observe or what we will get is that. So for 1, for H plus, as we have got from here, times SO4 2 minus is your 1.8 times 10 to the power minus 2 divided by, again, HSO4 minus has come out as 1, and this is the Ka2, nothing but Ka2. So is equal to 1.2 times 10 to the power minus 2. So if you calculate, I'm sorry, there was x. So if you calculate this, the x will be coming out as 0.6 times 10 to the power minus 2. So as x has come out as 0.6 times 10 to the power minus 2, SO4 2 minus concentration must be from here 1.8 times 10 to the power minus 2 minus x. If you put the value of x here, you will get the SO4 2 minus concentration as 1.2 times 10 to the power minus 2. Now we will be considering the dissociation of lead sulfate, right? So if you write down the dissociation equation, it will come out as Pb2 plus SO4 2 minus, right? Now if the solubility of the lead sulfate, we assume that as S molar, then the concentration of Pb2 plus is S and the concentration of SO4 2 minus is equal to S plus 1.2 times 10 to the power minus 2, which can be equal to 1.2 times 10 to the power minus 2. If you take the condition that S is much less than 1.2 times 10 to the power minus 2. So, for the solubility product of lead sulfate, which has been given in this part, so we have the concentration of Pb2 plus and SO4 2 minus. We have to multiply to get the value of S, and the solubility product has been already given. So for the final part, straight from here, we are solving in this part here, the final part. So S, that is the concentration of Pb2 plus times the concentration of SO4 2 minus, that has come out as 1.2 times 10 to the power minus 2. So this is nothing but the solubility product of the salt lead sulfate. So this has been given as 1.6 times 10 to the power minus 2. From here, you will get for S as 1.6 times 10 to the power, I'm sorry, it was given as 1.6 times 10 to the power minus 8. Right? Yeah. So 1.6 times 10 to the power minus 8 divided by 1.2 times 10 to the power minus 2. Now if you solve, you will get 1.33 times 10 to the power minus 6. So this is the value of S, which has been given here as your x times 10 to the power minus y molar, right? Now if you match this given part with the result that we have obtained, you will be able to see that x is equal to 1.33 and y is equal to 6. So we are to calculate the value of y, that is nothing but 6. So in the blank we have to put the value of 6. That is the value of y is 6. So very simple. I hope you have enjoyed this problem. Let's move on to the second one. And this problem has been taken from Joint Entrance Main Examination 2019. So this problem is actually based on the concept of freezing point depression. Before I start the problem, let's just talk a little bit about the freezing point depression. So what basically freezing point is? Freezing point is the temperature at which any substance and its solid and liquid forms are having the same vapor pressure. Now it has been observed that the freezing point of any solution is having much less value than the pure solvent. And this is actually called the depression in freezing point. Now, freezing point depression has many interesting and valuable or useful examples in your everyday life. Let's just talk a little bit about some of them. So, if I talk about the de-icing of ice-covered roads, you know, after heavy snowfall, overnight snowfall, the roads are basically covered with snow. But it will create problem for the cars to move. So that's why de-icing of the snow-covered roads are very, very important. So what is actually happening here? So I think you have seen the fact that whenever you are adding salt, for example, sodium chloride or calcium chloride basically, to your ice crystals, it quickly gets melted. And this is called the de-icing process. So on the snow-covered roads, if you pour such salts like sodium chloride or calcium chloride, it will immediately get melted because of the concept of freezing point depression. Although the freezing point of snow is 0 degree, but if you add salt to it, it will get melted and the freezing point of that particular solution immediately drops. And that actually helps for the cars to move quickly. And this is actually the very common and very useful application of freezing point, concept of freezing point depression. Now, if you consider the animals who are actually living in cold climate or snowy areas, their bodies are having an anti-freezing proteins, which are actually help them actually to bind of their blood snow crystals, and this actually prevents the crystallization. And this actually helps these animals to live peacefully in the very cold climate. This is also an example of freezing point depression. Now, if you have heard about vodka, and I don't know if you have seen, vodka can be kept at your freezer in liquid state forever. Why so? Because you know that vodka is containing alcohol, basically the ethyl alcohol or ethanol, and water. It is a mixture of ethanol and water. Although the freezing point of water is 0 degree centigrade, but the freezing point of ethanol is much less than that, which is about minus 114 degree centigrade. So because in vodka ethanol is present in significant amount with water, so all the vodka freezes at that particular temperature, that I have mentioned, that is minus 140. But in general freezer, which are actually kept at around minus 17 degrees centigrade, vodka will never get freezed, and your vodka can be kept at your freezer in liquid state forever. Let's take the final example. So now, if you consider the ocean water, so if you have checked or seen that never ever, even in very cold weather, cold climate, ocean water entirely don't get freezed. Why so? Even if the temperature is much below minus 0 degrees centigrade. Why so? Because of the fact that ocean water is actually salty. And so, even if the temperature of climate is much less than 0 degrees centigrade, because of the fact or that I have discussed about the freezing point depression, the temperature of the water, the salty water, will never get down to 0 degree centigrade, which is the freezing point of water. So, in between, the most of the water, ocean water, remains liquid even if the temperature is much below the 0 degree centigrade, that is the freezing point of the pure solvent water. So I hope you have understood the concept of freezing point depression in your day-to-day life. Now let's get started with the problem. This problem is also showing you the very really a problem which you are actually observing in your day-to-day life, that is mixing of milk and water. So we are actually worried about our milk sample which are consuming in our daily life. So I hope after solving this problem we will be able to solve such problem. So let's get started with the problem. So problem 2 is asking the freezing point of a diluted milk sample is found to be minus 0.2 degree C, while it should have been minus 0.5 degree C for pure milk. So the freezing point of a pure milk sample and a diluted milk samples are given. Now they are asking how much water has been added to pure milk to make the diluted sample. Some options are given. Option A is 2 cups of water to 3 cups of pure milk. Option B is 1 cup of water to 3 cups of pure milk. Option C is 3 cups of water to 2 cups of pure milk. And option D is 1 cup of water to 2 cups of pure milk. Now let's see how can we solve this problem. So we have to focus on the information that actually are given, and based on that we can be able to solve the problem. So we know that depression in freezing point that is delta dF can be written as TF0 minus T or TF. Now also we know that delta TF is equal to Kf times M times R. So this is the depression in freezing point, and Kf is your molar depression constant, A is your molarity, and I is Van Hoff factor. Now, this molarity can be expressed in the following manner. Weight of solute times 1000 divided by mass of solute times weight of solvent in gram. Right? This is the expression of molarity. Now, let's consider the diluted solution, diluted milk sample. So, using the following formula that I have written here, what can we write? So, delta TF, from here we will be able to solve. So, delta TF is equal to 0 minus of minus 2 degree C, or is equal to plus 0.2. Right? This is our delta T. So we will directly put this value in here. So 0.2 is giving you KF times, because in this case milk is your solute and water is your solvent. So W milk times 1000 divided by mass of milk times W1. W1 is the weight of the solvent, that is water, that has been considered for the diluted milk sample. So W1 water times, we know that the Van factor is 1. Okay, so you can number this problem, this equation as equation 1. Now, similarly for pure milk sample, what can we write? We can do the same thing for the pure milk sample. So here also your delta TF is equal to 0 minus of minus 0.5, which has been given here, the previous one. Right? So this is giving you the value of 0.5. Now similarly we can write the expression here, that is 0.5 is equal to KF times W milk times 1000 divided by mass of milk times W2, which is considered for the pure milk sample. The weight of the water W2 has been considered for pure milk sample, and Van factor is 1 again for the same sample. So let's number the equation as equation 2. Now if we do 1, or maybe here, if we do 1 divided by 2, what we will get? So 0.2 divided by 0.5 is giving you KF by KF times W milk times 1000 divided by mass of milk times W1 water. Now, as we are dividing, so from the equation 2, the lower part will go upside. So we will get mass of milk times W2H2O divided by W milk times 1000. And Venter factors for both the solutions are 1, so they are not appearing in this expression. So you can see from here they will cancel out, and milk will also get cancelled out. So we end up with this 2 also. So we end up with 0.2 times 0.5 is equal to, on top we have W2H2O, which we have considered as the weight of the water or the solvent in our pure milk sample, and in the denominator we have W1H2O, which we have considered for the diluted milk sample, the weight of the water in diluted milk sample. So this is giving you 2 by 5 is equal to W2 water in pure milk divided by W1 water in diluted milk. So you will be able to say that from this expression, which is our final expression, that 3 cups of the water is mixed with 2 cups of the pure milk. Now if you check the option C would be your correct option. So if you know the freezing point of the diluted milk samples and pure milk samples, this is the way you should be able to calculate how much water has been added to your milk sample. So I think very helpful and very interesting problem. I think you have thoroughly enjoyed this live session. Now I would like to share some more information with you. 11th June at around 9:30 a.m., this is a Sunday, we are arranging a demo class in our Aptdemy office, Lake Town. So interested students who are really interested and really are following us in Facebook or YouTube, so please come, and this is a free demo class. So please come with your parents and join us, so you'll be able to get in touch with us. And if you want to see the details, you can please check the description box. And also we are arranging these live sessions on a regular basis. So who are not observing this, watching this live class right now, you can check the checklist of Aptdemy, and there you will be able to see all the videos. So I hope that you have enjoyed this live session. So thank you very much for your attention. I will see you soon. Thank you very much. Have a good day. Thank you. Bye-bye.